March 2021, paper 6, variant 2. Question 1, student investigates the motion of an oscillating meter ruler. He uses the apparatus shown. The student ensures that the meter ruler is horizontal. Briefly explain or briefly describe how to check that the meter ruler is horizontal. How can he make sure that it is fully horizontal? He needs to measure the distance. One of the easiest methods is to measure the distance on either side and make sure that these two distances are equal. So I can measure this distance and this distance, okay, and make sure that they are equal. So measure hmm, the distance from the ruler, okay, from the ruler to the bench on either side, bench on either side, and make sure that they are equal. Make sure they are equal. Again, uh, you can use a set square to also make sure that it is perpendicular. Yes. Student moves these stands so that the vertical threads are at the marks on the meter ruler shown. Calculate the distance. Can I find the distance between these two marks? Yes. First distance on the first mark was at 2 and the last one was at 98. So the distance is 98 minus 2, which is 96 centimeters. He twists the meter ruler a small amount, as shown, and then lets it go so that it oscillates in a rotating motion. So keeps on oscillating back and forth. He measures the time t for 5 complete oscillations, which is 3.63 seconds. Suggests why is it useful for a trial reading for this experiment. Okay? This is a new question. Okay, it hasn't been. They didn't give this question before, so this is a new question. Suggests why is it useful to take a trial reading. Why should I take a trial reading? Well, just simply to make sure that I can actually conduct this experiment, that I can actually measure the time taken, measure the period of this oscillation, and go on with my experiment. This experiment requires him to measure the time taken for these oscillations. So he needs to make sure, first of all, that he can actually take the time, that he can actually measure this time, right? So this is why this trial reading is necessary, okay, to actually make sure, okay, to make, okay, sure, he can, okay, actually conduct the experiment and measure the time, okay, and measure the time. Again, okay, why is it necessary that he needs to take this trial reading? This is a trial reading before conducting the experiment. For example, when I want to go and buy a car, why do I take the car for a test drive? Why do I take the car for a test drive? To make sure that I actually like the car, to make sure that the seating is okay, that I can actually drive it quite carefully, that it's very quite fun to drive or whatever. Okay, so that's why you take the car for a test drive. This is the same thing for this experiment, that he's testing the experiment before actually going on with the experiment. He has a hypothesis. He has something in his mind. He wants to reach some sort of conclusion. Okay, to reach this conclusion, he needs to conduct this experiment, and to conduct this experiment, he needs to measure the time. So first of all, he has to make sure he can actually measure this time. What if, for example, he said that this meter ruler oscillates for 5 times, right? It oscillates for 5 times. What if, for some reason, these 5 oscillations were too little? For example, okay, the time taken was too little. It was 0.1 seconds or 0.2 seconds, whatever, right? That would be too short of a time for him to actually go on and conduct this experiment, right? So that's why he needs to actually make sure he can conduct this experiment. He can actually measure the time. That's why he conducts this trial experiment. Okay? Um, okay. Now, The student carries out the same procedure for values of 20, 30, and 50. Can I find for distance d equals 20 centimeters? Can I calculate and record in the table value of 1 over t, where t is the time of one oscillation of the meter ruler? T is what is the time of one oscillation of the meter ruler. Can I find the time of one oscillation of the meter ruler? What is t? What is small t? 17.85. What is 17.85? This is the time for 5 oscillations, right? Use the value of t, right? He gave you the equation. He actually gave you the equation. Can I find? Yes, you can find t. You can find 1 over t. 1 over t would be equal to 5 over small t. 1 over t would be equal to 5 over small t. So basically, you need to calculate 5 over 17.85, right? 5 over 17.85. What is this number? It is 0.28. It's 0.28. He gave you the equation. You do not need to actually think about it. If you wanted to think about it, you would have been able to think about it. Why? Because this time is actually the time taken for 5 oscillations. So you need to divide it by 5 and then take the period and say 1 over period, 1 over t. It would have been the same value, 0.28. This is the value of 1 over period, 1 over capital T. Okay, now I need to plot a graph. 1 over, so d slash centimeters on the y-axis, d slash centimeters on the y-axis, and 1 slash t over, okay, 1 t, 1 s on the x-axis. And now, for the time, for the distance, first of all, 20, 30, 40. Okay, so we have 20, 30, 40, 50, 60. That's easy. For the 1 over period, you want to start from 0.28 all the way to 0.88. I think it would be reasonable to start with 0.2, 0.4, 0.6, I'm sorry, 0.8, and then 1.0. Yeah, this would be an okay scale. First point, 20 and 0.28. Okay, let's zoom in a bit. 20 and 0.28, so 0.28 is at this point exactly. And then 30 and 0.44, 0.44, okay. 40 and 0.57, 0.57, okay. This is 30, 40 and 0.57. 50.72, 50 and 0.72, 60 and 0.88, 60 and 0.88, which is exactly at this point. Can I draw a line of best fit and find the gradient? G, yes, line of best fit, and then find the gradient, line of best fit. This is an easy line of best fit. Okay. Yes, this is a decent line of best fit. And then to find the gradient, you need to use the triangle method by joining two very distant points. So if I pick these 2 points and find the gradient, which is rise over run, 60 minus 20, 0.88 minus 0.28, right? 0.88 minus 0.28, 66.666, or you can say 67. This is the gradient. I'll remove this line. Okay, this is the gradient, 67. Explain why is it more accurate to measure the time for 5 oscillations rather than 1 oscillation? As you increase the number of oscillations, what happens to the human error? What happens to the percentage of the human error? The percentage of the human error decreases. So this is, you have this human error, which is kind of constant. So you actually need to decrease the percentage of this human error. To decrease, okay, the percentage of the human error. Describe how this experiment could be improved. How can I improve any experiment? How can you improve any experiment? By taking more readings, right? And then repeating and taking average. Okay, so you take more readings and repeat and take average. Take more readings and repeat and take average. Okay. The student investigates the cooling of hot water in two different cups. Cup A is made from thin plastic. The top of cup A has an inside diameter of 7 centimeters. Cup B is made from an expanded polystyrene, different material, and the top of cup B has a diameter of 8 centimeters. It's slightly larger. Can I find theta R? Yes, the room temperature would be 23 degrees Celsius. 23 degrees Celsius. One precaution that you would take while taking the reading, you need to take a precaution, which is take the reading perpendicularly to avoid the parallax error. One very, very important precaution. Take the reading perpendicularly to avoid, okay, parallax error. And then volume of 100 centimeters cubed is poured into each cup. Complete the table headings, so the time is in seconds. Takes the reading every 30 seconds, so time is in seconds. Temperature in degrees Celsius. Write a conclusion stating which cup A or B is more effective in reducing the cooling rate. Which cup is more effective in reducing the cooling rate? Let's see. In A, it was 87.5, ended up being 77, so the difference is 9 point or 10.5, right? Difference is 10.5 degrees, right? And then cup B was 88 and it's 80.5, which is a difference of only 7.5 degrees Celsius, right? 7.5 degrees Celsius. So it seems that cup B is a little bit more effective, right? Cup B is more effective since the difference okay, since the difference in B is, and you need to write down the numbers, 88 minus 80.5, which is 7.5 degrees Celsius, while the difference, okay, difference in A is, again, you have to write down the numbers, 87.5 minus 77, which is 10.5 degrees Celsius. You have to write down, whenever he says justify your answer by reference to the results, you have to write down the results which are given in the table. You have to write down the difference between these results, okay? Hmm. Can I find XA? Can I find the rate of cooling in A during the whole 180 degrees, 180 seconds? Yes, theta 0 minus theta 180, 87.5 minus 77 divided by the time, total time, which is 180. Okay. 87.5 minus 77 divided by 180, which is 0.058 degrees Celsius per second. Again, do not forget the unit. Suggest an additional experiment to show how the lid affects the cooling rate of cup A. Explain how to use these additional results to show the effect. How does the lid affect the cooling rate of cup A? How can I conduct a further experiment? By repeating the same experiment but without the lid. Why? Because I need to compare. Does the lid actually does it actually affect the rate of cooling or not? Right? And then we have to find the difference between these two cooling rates. So XA was 0.058. If you remove the lid, I guess that the cooling rate would increase, wouldn't it? It would definitely increase, yes. So you have to find the difference between them and test whether they are actually different. If they're very close, so they're not different, you can consider them to be the same or not, right? So the additional experiment would be to repeat, okay, the experiment without the lid. And then the explanation, measure or calculate actually. Calculate the rate of cooling without the lid and find, okay, and find the difference between it and the and XA, which is the initial rate of cooling, and XA. Student wishes to compare the effect of the materials, suggest two variables that should be constant. What are two controlled variables? The volume of the water and the initial temperature. Yes, initial temperature of the water and the volume of the water. Right? Hmm. Question 3. So he investigates a resistor and lamp connected in series. Have a crocodile clip, and then measures, moves the crocodile clip and finds the voltage and finds the current. Read and record the values of I and VR. Okay, VR, which is the voltage across the resistor. VR, or the voltage across the, yeah. So I is what? I is 0.18. 0.18. VR was 3.7, right? Yes, it was 3.7. He repeats the steps for VL 1 volt, VL 0.5 volts. Okay, so he keeps on changing the voltage of the lamp and measures the voltage of the resistance. Calculate and record RL. Can I find RL? Yes, I can find RL and RR. RL would be VL over I, or R would be VR over I. So for RL, again, VL over I. So VL 2 divided by 0, 0.18, for example. So the first one in this RL is what? Is 2 divided by 0.18. This is for the first one, which is what? What's 2 divided by 0.18? This is 11.1, right? This is the RL, first RL. 11.1. 11.1. And then the second one would be 1 divided by 0.15. 1 divided by 0.15. What's 1 divided by 0.15? This is 6.67. Okay, 6.67. And then the last one would be 0.5 divided by 0.5 divided by 0.12. This is 4.16 or 17. 4.17. So this is R L. Can I find R? R, yes, 3.17. 3.7 divided by 0.18. 0.18, which is 20.6. And then 3 divided by 0.15, 20. Okay, this is 3 divided by 0.15. And the last one is 2.4. 2.4 divided by 0.12. What is 2.4 divided by 0.12? This is again 20 ohms. Describe the pattern. Describe the pattern of any change in the value of RL as VL decreases. As VL decreases. What happens to RL? RL is also decreasing. They are directly proportional, right? As VL decreases, RL decreases. As VL decreases, RL also decreases. Why? Because they are directly in proportion. Hmm. Sunt suggests that RR should be constant. Is this true? RR. So we have 20.6, 20, and 20, which is quite obvious that they are constant. Even 20.6, is it different? No, it's not different. It is within the limits of experimental accuracy. How can I calculate the limits of experimental accuracy? 20.6 divided by 20, which is 1.03 if I'm not wrong. 20.6 divided by 20. Yes, it is 1.03, which is 3%, right? This is a 3% difference, which is definitely within the limits. So are they constant? Yes. Okay. Yes, they are constant. Can say agree they are constant. Why? Because 20.6 and 20 are close. The values are close and they are within the limits. Okay, within the limits of experimental accuracy. Okay. Hmm. Okay. A student wishes to determine the resistance of lamp RL when the potential difference across the lamp VL is 0 volts. Wants to determine the resistance when the potential difference is 0. Describe how the experiment can be extended to do this with the help of a suitable graph. With the help of a suitable graph. So I want to find the resistance of RL when the voltage is 0. You say the resistance is 0. Well, you can't actually make sure that the resistance is 0. How can you make sure? From the graph? You have to draw a graph. You have to plot a graph. You have to plot a graph with the resistance and voltage. With the resistance and the voltage. So you actually need, if I check the table, let's take a look at the table. You have three values, VL, and three values of RL. Are these enough? No, definitely they are not enough. So you need at least 5, 6 values of the voltage and the resistance to be able to actually draw the graph. So you need to get more values of V and R and then plot the graph of the voltage and the resistance and then extend the line, extend the graph until it reaches the RL when the RL until it reaches the RL axis, which is what is the RL axis? If you draw a graph of RL and VL, RL and VL, where is VL? hmm, Where is VL equal to 0? So VL would be equal to 0 here, right? VL would be equal to 0 here. So wherever this line meets the RL axis, wherever the line meets the RL axis, this would be the value of the resistance when the voltage is equal to 0. This would be equal to the resistance when the voltage is equal to 0. So you need get more values for VL and RL, and then RL, and then plot a graph of VL and RL, extend the line until it meets the RL axis. RL axis. At the RL axis, this is when VL is actually equal to 0. Hmm. Now, it is possible to use a variable resistor instead of resistance wire to change the potential difference across a lamp. Complete the circuit to show a variable resistor used for this purpose. The voltmeter connected to measure the potential difference across the resistors. So across the resistor, you need a voltmeter, and then you need a variable resistor in series, and then just complete the circuit. Hmm. It investigates the motion of a ball rolling down a slope. Plan an experiment which enables him to investigate how one factor affects the average speed of the ball. One factor. Whatever factor. So you have several factors that could affect the speed of the ball. Yes, you do have several factors. The apparatus available includes balls of various sizes and materials, a board which can act as a slope, blocks to support one end of the board. So basically you have the slope, right? You have the slope, and then you have the ball, which would roll down, and then you need to measure the average speed. You have the equation, distance, and time. You have several missing apparatuses, right? You do have several missing apparatuses, such as the ruler, such as the stopwatch. What is one factor that might affect the speed? You have several factors. For me, I would take the mass of the ball to be the factor. Why? Because it's an easy factor to measure, right? It's an easy variable. You can measure the mass easily. So you would actually need a balance as well. So this factor is the mass of the ball, and then I write down several masses, several suitable masses for this experiment. The range of values would be the mass of the ball, and you need several masses. Let's take 50 grams, for example, 100 grams, 150, 200, and 250 grams. Different masses for the balls. And then, what are the constants? What are the controlled variables? The controlled, okay, variables. If I want to change the mass of the ball, if you want to change the mass of the ball, then the slope has to be constant, right? The slope has to be constant. What else? You could say, for example, that um, the surface, okay, the surface of the slope has to be constant. You can't change the surface. Why? Because if you change the surface, then the friction would differ, and this would affect the speed of the ball, right? Um, but that's the material of the ball. Yes, it could be one factor. Yes, it's controlled variables, the slope, okay, or you can say the angle if you want to say angle instead of slope. Okay, the surface of the board. Okay, the surface of the board, the material of the ball. Okay, what are the missing apparatuses? Missing apparatuses could be the ruler, meter ruler, the stopwatch, and the balance. Again, let's check the points. So we stated the factor, we wrote down any additional apparatuses, the key variables. We need to state how can we conduct this experiment, table, and then the conclusion. You may draw a diagram. You may draw a diagram if you want. Steps. Controlled variables actually could be, one of the controlled variables would be the distance traveled by the ball. Yes, the distance traveled by the ball. Okay, distance traveled by the ball on the slope, for example, on the slope. So if let me draw a diagram for you to understand the distance I'm talking about. So you have the slope, okay, and then which is supported by a wooden block from this point. This is the starting point. Let's say this is point A and this is point B, for example. So I have point B, A and B. This is a fixed distance. The ball has to start point A. This is the starting point. Okay, starting point, and this is the ending point or the finishing point B. So this is a fixed distance. You cannot start the ball, you cannot release the ball from any point other than point A. It has to start from point A specifically. Okay? So this has to be a constant. This has to be a controlled variable. Steps: release the ball from point A, okay, or release the ball from a fixed point, from a fixed point. Measure the distance or measure the time. Okay, measure the time taken to travel a fixed or a constant distance. Okay, calculate the speed. Calculate the speed, which is equal to distance over time. You have to write down the equation. Okay? And then after you calculate the speed, repeat and take average. Okay, repeat, repeat, and take average. These are the steps. Can I draw a table? Yes, I can draw a table. Yeah. This is the table. The variable that you are changing is the mass of the ball in grams. You have the distance in, let's say, centimeters, the time in seconds, and then the speed in meters, sorry, centimeters per second. Centimeters per second. For the conclusion, you need to write down for each value of the mass. For each value of the mass, repeat the experiment. Repeat the experiment and take average. Take average. Record the results. Okay, record the results in a table and compare the results. How can you compare the results? You have to plot a graph. You have to draw a graph, okay, by plotting a graph of what? Of the mass versus the speed. And compare whether the mass does actually affect the speed or not. Okay?